Welcome to the lecture 10 of Financial Econometrics, and we are continuing our discussion on the regression assumptions. So moving towards the contents, we had previously discussed three assumptions of a regression model, a classical linear regression model. The rest assumptions will be discussed in this lecture. That is, no autocorrelation, the n should be greater than number of parameters. We have the non-constant assumption, non-constant x assumption. Then we have multicollinearity, no multicollinearity, exogeneity. So starting with no autocorrelation, symbolically it can be written as the covariance between the error term and the subsequent value should be 0. And this assumption simply states that there should be no correlation between different values or subsequent values of the error term. So normally this issue is not specific to cross-sectional data, and we had our discussion on cross-sectional data, what cross-sectional time series or panel data is. This type of problem, this no autocorrelation problem, is specific to the time element. Whenever there is a time element, it can be that the autocorrelation problem can be there. That means this no autocorrelation assumption can be violated in the time series data. Now this no autocorrelation assumption is also called no serial autocorrelation, no autocorrelation that we have just seen, or independent error term. So this assumption says that there should be no autocorrelation, and by auto it means that the correlation of the error term by itself. So correlation is the correlation and auto represents the term by itself. So when this assumption is violated, then we would say that there is an error, that there is an issue of autocorrelation or serial correlation in our data. So for example, we have the time series data of say GDP, or we have time series data of say for example stock index or stock prices, stock returns, index return. So whatever that variable is, we have certain values, and it is that in most cases that those variables, so today's GDP or today's price would be dependent on yesterday's price, right? So that effect would also be seen in the error term. This is error term, and if that happens, that the error term at time if the error term at time t is related with the error term of time t minus 1 or time t minus 2, it simply means if the error term is related to the previous error terms, then we would say that there is the problem of autocorrelation, and it would violate the assumption of no autocorrelation. There should not be this issue. So the error term should not be related by with the previous error terms. Okay, so each successive error term is independent of the last error term, and that's why it is called independent error term. The error term should be independent. This error term should be independent of this error term, and this error term should be independent of the previous error term, and so on. And normally this issue occurs in the time series data that we have just discussed. Cross-sectional and cross-sectional data, this problem won't normally occur. So by looking at these three images, so if we can see here, the error terms are positively correlated with one another. So, and in this case, the error terms are negatively correlated. What we want is neither of these patterns. We do not want any of these patterns. We just want, or if in some cases, if there is this kind of a pattern, right? This is our regression line, and these are our observations or error terms, the difference between them. So we do not want any kind of pattern. We just want that they should be independent of each other. So the error term in this case are independent of each other. They do not have any specific pattern. And when there is the problem of autocorrelation, then the standard error becomes unreliable. Okay, and we would discuss in detail each of these assumptions. They would have a lecture of their own. So moving on to next assumption, n should be greater than the number of parameters. It simply says, this is the simplest assumption, and it says that the number of observations should be greater than the number of parameters. So for example, if I have a model where I have one dependent variable and then I have a constant term and then there is one independent variable, then at least to solve this equation I should have two observations. And if I have a model where I have one dependent variable and two independent variables, beta 2, x2, then in this case, because I have two parameters, right, to solve, my number of observations should be greater than the number of parameters, right? And so two parameters cannot be estimated with single observation. We have just discussed it. Okay, moving on, the non-constant x value. So there should be variability in the explanatory variable, and it means that if there is a explanatory variable, there is a x variable where all the values are same. So it isn't a variable, it is a constant, right? So in this case, what would happen is that the mean of this variable would also be 5. And when we calculate this beta value, our parameter, then in denominator you would notice that we have x minus x bar, right? So for each value we would have x minus x bar, and we would take square, but it doesn't matter because the answer would be 0. 5 minus the mean is also 5, so the answer would be 0. Doesn't matter we take the square or not, the answer would again be 0, and their sum would be 0. So this denominator would become 0, right? And due to that, we would not be able to estimate our parameters. So the x should not be constant, and irrespective of the mathematical limitations, it is quite intuitive, right? Our objective is to explain the variation in y. So there are some variation in y. Say for example, this y variable, our dependent variable is salary. We are saying that the salary variable varies. For some people the salary is 10,000 and for others the salary is, say for example, 12,000, right? So there is variation in this dependent variable. And for others the salary is, say, 13,000. So there is a variation in this dependent variable, and what we are basically doing with this whole exercise of estimating the parameters, and we are trying to explain this dependent variable, and we are trying to explain what is causing this variation in dependent variable. So let's say we came up with the idea that education, the higher the education, the higher will be salary, and this variation in education is explaining the variation in salary. So if there isn't any variation in x, or say even if in y, say all the y terms are same, we have all the people having same salary, then again that wouldn't be possible to estimate this term. So we are trying to estimate find out the variation in y that is being caused by variation in x. If there isn't any variation, then there is nothing to explain. And remember, these are variables. So variables must vary. So this x and y term should vary. That is the assumption. Okay, moving on to our next assumption, which is multicollinearity. And this simply says that all the x terms, and by x terms we mean the independent variables, they should not be related. Their correlation at least should not be, they should not be perfectly correlated, right? So this assumption says that there should not be perfect multicollinearity. There can be some kind of correlation between the independent variables, that would be there, but there should not be multicollinearity. And when there is perfect multicollinearity, then even our model starts to shut down, right? It doesn't allow us to run the model. So what correlation is? Remember, it is the relationship or association between two variables. So in this case, we are trying to say that we have, let's say, x1 and x2. We have two independent variables in our model. Say, for example, our model is y is equal to alpha plus beta 1 x1 plus beta 2 x2. So in this case, what we are saying that these two independent variables should not be correlated, right? So multicollinearity occurs where x variables are themselves related. In autocorrelation, remember, the error term was related to its previous error term, but in multicollinearity we are not discussing the error term. We are talking about the independent variables, the explanatory variables by themselves. So the independent x term, it is also called independent x terms. The x terms aren't related to each other. And this is quite interesting example. Say, for example, our dependent variable is car accidents. We are trying to explain what causes car accident, and in this case we have taken two independent variables. One is the number of cars and other is the city population. So we can say that the higher the number of cars, the higher the chances of car accident, and the higher the city population, the higher the chances of car accident. But if you would see that, you would notice that the higher the number of residents, the higher would be the number of cars. So you would notice that there is a multicollinearity issue. I mean, the number of cars isn't independent of the second independent variable, which is city population. It can be that it can't happen that the number of cars can keep on increasing where the city population would remain constant, right? So these two terms are related. These two independent variables are related, and somehow some part of the information that they are providing isn't unique. So some part of information isn't unique. They are independent. Now remember, when we are interpreting the beta, the parameter, this beta parameter, the slope, say for example in this case the parameter is 2. So our interpretation of this parameter would be that as the number of cars increase by 1 unit, that is plus 2, the probability of car accident would increase by 2%, say for example, or the car accident would increase by 2 units. Now remember, at the end of this interpretation, we always say keeping other things constant. So now you would notice this problem with this multicollinearity case, that in this case we cannot say that term. We cannot say that keeping other things constant, because you can't keep the number of residents constant, number of population constant, while keep on increasing the cars. So you can't keep the other variables constant. So you get an idea that in case of multicollinearity, the independent variables aren't independent, right? So some part of information they are presenting, both the variables are presenting some part of information. So normally when that happens, we sometimes drop a variable, but that is the case when we have perfect multicollinearity. But in case of when there is a low correlation, then normally that doesn't happen. So you get the idea of multicollinearity. And when this assumption of no multicollinearity is violated, then we say that we have a problem of multicollinearity. So that shouldn't happen. The assumption says that there shouldn't be any problem of multicollinearity. So moving on to our last assumption of exogeneity, and the basic idea of exogeneity is that the x term and the error term should not be related, right? So the x term and the error term shouldn't be related, and let me first present an example. So again, coming to our example of salary. So we say that salary is dependent on the number of years of education, and obviously error term. And what this error term is, all the variables that we haven't included in our model, their effect would be summed in the error term. And let's just say, let's just take the variable of socio-economic status of a person or a family, or say the IQ level of a person. So if you take socio-economic or IQ level variable, then those variables affect salary, right? The higher the IQ, it's more likely that that person would have a higher salary, or someone coming from a good socio-economic background, they would have a higher salary. But these two variables also affect our, now because we haven't included this socio-economic or the IQ level variable in our this equation, this model, then their effect is in the error term. Now moving on, we know that IQ level or socio-economic factor would also affect the number of years of education a person would get. So someone coming from a good socio-economic status, then there is a higher probability that they would have higher education. Someone having a higher IQ or ability would also have a higher number of years of education. So now we see that there is a variable z. It can be socioeconomic status or it can be IQ level. It is affecting both the salary, the dependent variable and the independent variable. And when it is affecting the dependent variable and we haven't included it in the model, then its effect is in the error term. So we can say that there is a variable z which is affecting the error term and the number of years of education. So when that happens, the independent variable and the error term would be correlated, and so this error term isn't strictly exogenous. By exogenous we mean that it isn't coming from outside of the model. So in our case, the independent term, which is the year of education, is not purely determined from outside of the model. Some part of it is determined, is affected, is function of the error term. So the assumption of exogeneity says that the x variable should give us the information that is completely external, it is exogenous to the rest of the model. It should not be determined from error term. And when this exogeneity assumption is violated, then we have a problem of endogeneity. And we say that this independent variable is determined from something that is within the model. We do not want that to happen. So our assumption of exogeneity is violated. Now the case that we have just discussed is the case where we have omitted a variable from the model. We haven't included that variable in the model, in this case our z variable or socioeconomic status or the ability of a person. And this endogeneity issue is being created due to that omitted variable, which we call omitted variable biasness. We would discuss on it in later lectures. It is not just the cause of exogeneity. There are other causes. Say, for example, we have measurement error in our independent variable, or say we have reverse causality. So in this case, say salary is affecting number of years of education. The higher the income, the higher would be the number of years of education. Or years of education is also affecting salary. The higher the number of years of education, the higher would be the chances of getting a good salary. So in this case, we can see there is a reverse causality. Not just the X is affecting the Y variable, the dependent variable is also affecting the independent variable. So what I mean to say is that the problem of endogeneity is not just related to omitted variable biasness. It can occur from other reasons, and again we would have a whole lecture on exogeneity, and there we would discuss how exogeneity occurs, what are the reasons, what are the signs of exogeneity, how can we measure it or test it, what are the diagnostic tests, etc., and what are the remedies for it. And lastly, we will discuss BLUE estimator, and BLUE stands for Best Linear Unbiased Estimator. Now remember this thing, this beta hat, remember we use hat when we have an estimator. We have estimated this value using certain methods. Say for example, in this case we have used OLS, and we know there was a formula to calculate this beta hat that we discussed in previous lectures. Okay, so we want this estimator to be blue, and what blue means, it should be linear unbiased estimator. And of what we want this to be unbiased linear estimator of our true parameter, which is the beta 2. So the estimator should be linear. It should be linear function. It should be the unbiased, and by unbiased we mean that this beta hat should be equal to our population parameter. So our sample parameter should be equal to our population parameter. And lastly, it should have small variance. By variance we mean the dispersion should be small. So what we want is whatever estimator we calculate should be linear, should be equal to the true parameter, the population parameter, and should have small variance. An unbiased estimator with least variance would also be called efficient estimator. So when these two properties are there, the unbiased and the variance is small, then we would call it an efficient estimator. So estimator is blue if it is linear, unbiased, and more efficient than any other estimator. So let me explain this with the help of this graph. Say for example, we have this estimated value beta hat, and we say that the expected value of beta hat is equal to the true parameter, right? And this is the frequency distribution of this beta. And what this means by this frequency distribution, let's say we have a population of different people, and we take a sample. Say this is sample 1, this is sample 2, this is sample 3, and we have sample n, right? So from all these samples, using the formula that we have discussed previously, we calculate our beta value, we calculate our slope value. So this is beta 1, this is again beta 2, this is beta 3, these all are coming from different samples, and then we have beta n. So when we make a frequency distribution of all these betas, then we should have this bell-shaped curve, and we are saying that some would, because of sampling error, some would not be exactly equal to the population parameters, but majority of time we would have our estimated parameter, our estimator, OLS estimator would be equal to the population parameter. And this is what we are saying is unbiased. So the population, the estimator should be equal to the population parameter. Now this is another estimator, and we say, for example, this was calculated using OLS method, and this was calculated some other XYZ method. Now we would, if we put these graphs over each other, then you would notice that the OLS estimator is having less dispersion. There is a higher chance that we get a estimator that is equal to population parameter and unbiased estimator. But in case of the XYZ method, we have a higher variance. So which estimator would you like to have, the beta hat or the beta asterisk? Obviously they both have the same beta, they both are unbiased, but which one have the higher variance? The beta asterisk have higher variance, their dispersion is higher, so we would want to have a small variance. The variation should be small. So this last property, it says, this is what I am trying to explain, that the variance should be small. Although in some cases, if we have an unbiased estimator but the variance is higher if we compare it with another estimator, so we would like to have an estimator that would have a small variance. A blue estimator would be the one that would have all these properties. It would be unbiased, it would be linear, and it would have a small variance. So for example, if I have an estimator that has zero variance, it is linear, but it isn't unbiased. In that case, that estimator wouldn't be blue. So the idea of explaining this blue estimator was to make you understand this Gauss-Markov theorem. And what this Gauss-Markov theorem simply states is that we have seen that what is blue parameter, what is blue estimator, and we want all our estimator to be blue. They should be unbiased estimator. They should be efficient. So what this Gauss-Markov theorem says is that the OLS estimator, the estimator that we can calculate from the formula that we have seen, the beta 1 and beta 2 formula that we just saw in previous slides. This was the formula x minus x bar whole square and y minus y bar whole square divided by summation x minus x bar whole square. This is the formula that we use. Sorry, this square term isn't there in the numerator. Okay. So what we want is, what the Gauss-Markov theorem says is that OLS estimator, the estimator that we are getting is from this formula, if it fulfills the classical linear regression model assumptions, the CLRM assumptions. And what are those CLRM assumptions? The assumptions that we discussed in this lectures, the autocorrelation, multicollinearity, endogeneity, the normality of the error term, etc. If these assumptions are fulfilled, then the OLS estimator would always be blue. So we do not have to care whether our estimator is blue or not. We just have to fulfill these assumptions, and once these assumptions are fulfilled, the Gauss-Markov theorem have proved it, that the OLS estimator would always be blue.